Hello, this is Matt Dean, and today we're going to work some waves practice problems. Here's practice problem number one. We have a standing wave. It's produced in a vibrating string. Remember, standing waves are produced by interference between waves. The length of the string from end to end is 1.5 meters. And we have a vibrating motor that's vibrating at 60 hertz, 60 cycles per second. We want to know the speed of the wave. This is a situation where we're going to have to use the wave equation. The wave equation is that speed is equal to the wavelength of the wave times the frequency of the wave. Well, first of all, we have the frequency. The frequency is 60 hertz, so that's going to go there. The wavelength of the wave we can determine by knowing the length of the string. Remember that a standing wave, one wavelength is made up of two loops. So this is one wave. And then we've got another half a wave here. So what we're saying is the wavelength is essentially 2/3 of the string length. Well, the string length is 1.5 meters. So the wavelength is 2/3 the length of the string, 1.5 meters. So the wavelength is 1 meter. So if we go V equals wavelength, 1 meter, times frequency, 60 hertz, which is cycles per second. Sometimes we'll write that as second to the -1. Multiply that out, we end up with 60 meters per second is our speed for this particular wave. All right, here's practice problem 2. This was not really a problem, it's more of just a conceptual question. In general, the higher the frequency of the interfering waves that form a standing wave, the blank. First of all, the higher frequency doesn't necessarily have anything to do with a higher wavelength. Not necessarily a higher speed because the wavelength could get shorter. What it does have to do with is C. If the frequency is higher, that means there's going to be the interference between the two waves is going to occur more often. And that means there's going to be more points of complete destructive interference, which are nodes, and more points of complete constructive interference, which are antinodes. So C is our correct answer on practice problem number 2. All right, here's practice problem number 3. If a string fixed at both ends resonates in its fundamental mode, and remember that fundamental mode is the lowest frequency, it's the first harmonic that it will vibrate at. That frequency is 150 hertz. At which of the following frequencies will it not resonate? First of all, it won't resonate at a frequency lower than the fundamental. So that means 75. It will not resonate at 75. Also, for it to resonate, it has to be at in certain multiples of this frequency. So it will resonate at 300. It'll also resonate at 600 because those are multiples of 150. It will not resonate at 500 because 500 is not a whole number multiple of 150. So the question here asks us, which of the following frequencies will it not resonate at? And those are A and C. C because it's the frequency is lower than the fundamental frequency, and A because 500 is not a whole number multiple of that fundamental 150. All right, here's practice problem number 4. A computer simultaneously plays sounds of 525 hertz and 535 hertz. What beat frequency will be heard by nearby observers? So when two sounds that are close in frequency are played simultaneously, there's going to be this pattern of constructive and destructive interference. When the waves destructively interfere, the sound is going to get quieter. When they constructively interfere, the sound is going to get louder. To determine the actual frequency of the beat that you will hear, you subtract the frequencies of the two sounds. So in this case, we're going to go 535 hertz minus 525 hertz, and we're going to end up with a beat frequency of 10 hertz. So we should hear 10 beats per second. All right, practice problem 5. Two guitar strings both vibrate at 825 hertz. The tension in one of the strings is increased, and 5 beats per second are heard as both strings vibrate. What is the new frequency of the tightened string? All right, when a string has more tension in it, that increases the speed of the wave. Well, in this case, because the wave is moving faster, it's also going to have a higher frequency. Now we're going to have two waves nearby, simultaneously being played, one in each string, and they're going to start to interfere. And that's how we're going to get the beats. Now we saw in the last problem, to find the beat frequency, we're going to subtract the frequencies of the two sounds. We know in this case the difference in frequency is 5. We also know that that frequency in the tightened string is going to be higher than it was to begin with. It was 825. Now it's going to be higher. So the new frequency of the tightened string is going to be 830 hertz. Answer B looks good on practice problem number 5. All right, practice problem 6. The diagram above depicts a standing wave in a rope. Which harmonic is illustrated? All right, you can determine the harmonic number by counting the antinodes, the points of maximum constructive interference. So here's an antinode, 1, 2, 3. This is the third harmonic. So the number of antinodes is going to be equal to the harmonic number. The number of nodes in this case, the points of destructive interference, 1, 2, 3, 4. The number of nodes is always one higher than the harmonic number. All right, so here's another standing wave problem. The diagram above depicts a standing wave in a rope. What is the wavelength of the depicted wave? Well, remember, one complete wavelength in a standing wave is 2 of these loops. We know the string length is 60 centimeters. So one of our waves is essentially 2/3 of the string length. So we're going to take 2/3 of 60, and 2/3 of 60 is going to end up being 40. We're in centimeters. So our wavelength for this particular wave is 40 centimeters. One wavelength in this case is 2/3 of the string length. And again, remember that one wavelength is 2 loops in a standing wave. All right, this problem is related to practice problem 7. Here we have the same standing wave that we had in 7. We know the wave has a frequency of 725 hertz, and we want to know the speed of the wave in the rope. Again, this time we're going to have to use the wave equation, which is speed is equal to wavelength times frequency. In the previous problem, we found that the wavelength, 2 loops, is equal to 2/3 of the string length, 60. So that was 40 centimeters. So our wavelength is 40 centimeters. But notice that all our speeds over here are in meters per second. So 40 centimeters is 0.40 meters times our frequency of 725 hertz. We multiply that out, and we end up with 290, and our units are going to be meters per second in this case. So 290 meters per second. All right, practice problem number 9. We have a standing wave in a closed-end air column. And we're trying to find the fundamental frequency, the first harmonic, if we know the length of the air column, 50 centimeters, and we know the speed of sound in that air column is 340 meters per second. Well, again, we've got to use the wave equation. Speed equals wavelength times frequency. We're trying to find frequency, so we solve for frequency. Frequency is going to equal speed divided by wavelength. We know the speed is 340 meters per second. But we've got to find that wavelength. Well, what we're looking at in this picture is like 1/2 of one loop. And we know that that length is 50 centimeters. We know that one wavelength is made of 2 complete loops. So essentially this is 1/2 of a loop. So 4 of those, which means our wavelength is 4 times this air column length. So our wavelength is 200 centimeters. So we need to do this in meters per second. So 200 centimeters is 2 meters. So we're going to put 2 meters right here for our wavelength. So 340 meters per second divided by 2 meters ends up giving us a frequency of 170 hertz. All right, so another closed-in pipe standing wave problem. This time the pipe, the air column or pipe is 0.25 meters tall. We get a first harmonic at 349.2 hertz. We want to know the speed of sound in the pipe. Again, we have to use the wave equation. Speed is wavelength times frequency. We know the frequency. That goes here. Remember that a first harmonic is going to be the length of, it's going to be like 1/4 of a wavelength, and it's going to be the length of the air column. So this is the length of our first harmonic, which is 1/4 of an actual wavelength. So we need to multiply 0.250 times 4, end up with 1 as our wavelength. So our speed is going to be equal to 1 meter of wavelength times our frequency of 349.2 meters per second. So we're going to end up with a speed of 349.2 meters per second. Again, remember the first harmonic is 1/4 of a loop. So to find that wavelength, we need to multiply that 0.250 times 4 to get the wavelength of the actual wave. All right, so practice problem 11, we have a string of length 12 meters fixed at both ends, and we get a standing wave with 5 nodes. And we want to know the harmonic number and the wavelength of the wave. Well, first of all, remember the harmonic number is equal to the number of antinodes, or you can also find it by taking the number of nodes minus 1. So we have 5 nodes minus 1. We have the 4th harmonic. This is the 4th harmonic. If the wave has 5 nodes, it's going to have 4 antinodes. If it has 4 antinodes, that means it's consisting of 4 complete loops. Well, remember that one wavelength is 2 loops. So essentially on this string, we have 2 complete wavelengths. Well, the string is 12 meters long. We complete 2 wavelengths in that string, which means the wavelength in this case is half the length of the string. So we're dealing with the 4th harmonic and the wavelength of our wave, 6 meters, half the length of the string. Answer A looks good for practice problem 11. All right, so practice problem 12. We have a string of length 10 meters and mass of 300 grams. It's fixed at both ends. It has a tension in the string of 440 newtons. And we want to find the frequency of the standing wave for which the distance between a node and the nearest antinode is 1 meter. Right. First thing that we've got to do here is find the speed of the wave. And to do that, we're going to use this equation. The speed is going to be equal to the square root of the tension force divided by the mass of the string divided by the length of the string. So in this case, we have the tension, 40 newtons. We have the mass. Let's put that mass in kilograms, so 0.3 kilograms. And we also have the length of the string, 10 meters. We have to take the square root of that whole quantity. And when we do, we end up with a speed of 36.5 meters per second. Next, we can use the wave equation. V equals wavelength times frequency. We're trying to solve for frequency. So frequency equals speed divided by lambda. Well, we know the speed, 36.5 meters per second. All right, we can get the wavelength from the stem of our question. It tells us that the distance between a node and the nearest antinode is 1 meter. Well, the distance from a node to an antinode is essentially half of a loop. Remember that a standing wave is made of 2 complete loops. So this distance from one node to an antinode is essentially 1/4 of one wavelength. So if 1/4 of one wavelength is 1 meter, then a whole wavelength is going to be 4 meters. Our wavelength is 4 meters. So we take 36.5, we divide it by 4 meters, and we end up with a frequency of 9.13 hertz. So our answer on practice problem 12 is C. All right, so practice problem 13. The figure below illustrates standing wave patterns in 2 identical tubes which contain the same amount of water. The standing waves were produced by holding a vibrating tuning fork near the top of the tubes. What's the relationship between the wavelength of the wave in tube A and the wavelength of the wave in tube B? Well, notice in tube A, our standing wave is essentially just 1/4 or 1/2 rather of one loop, which means we're looking here really at 1/4 of one wavelength, which means the wavelength of this wave is essentially 4 times the length of the tube. We'll say 4 times L. Whereas down here, the wavelength's much shorter. Here we can see one complete wave right there, plus 1/4 of another wave. So that means in this string length, or in this tube length rather, we have 4/5 of a wave. I'm sorry, we have 5/4, which means the wavelength of this wave is essentially 4/5 of the length of the tube. So if we compare these two, what that tells us is that this wave is essentially 5 times the length of this wave. So let's look and find an answer here. It looks like our answer here is going to be D. Wave A is essentially 5 times longer than wave B. All right, practice problem 14. 2 square wave pulses located in the same plane move through the same rope. One of the waves has a maximum displacement of 6, and the other has a maximum displacement of 3 centimeters. Which of the following is a possible value for the displacement of the rope when the waves interfere with each other? Choose 2 answers. All right, when two waves interfere, their summed displacement has to equal the algebraic sum of the individual displacements. So if they're constructively interfering, if they meet crest to crest or trough to trough, we're going to get 6 plus 3, we're going to get 9 centimeters. So answer C is a valid answer. But we could get it where a crest of one of the waves meets a trough of the other. So we could get a 6 on top and a 3 on bottom, or vice versa. That's like adding +6 and -3, or -3 and +6. Either way, we're going to end up with an answer of 3. So if we get positive interference, we're going to get 9 centimeters. Negative interference is going to give us 3 centimeters. So on practice problem 14, we're looking at answers C and D. All right, so now we're on practice problem 15. The diagram above illustrates 2 identical tuning forks separated by a small distance. When the left tuning fork is struck with a hammer and begins to vibrate, the tuning fork on the right also begins to vibrate. So the sound waves travel, they have similar frequencies, resonant frequencies, so there's some forced vibrations. The tuning forks are now placed in a sealed chamber, and the air is pumped out of the chamber. The left tuning fork is again struck and begins to vibrate. Does the right tuning fork vibrate? Important thing to remember here is that sound waves, unlike light waves, require medium. They require air. So when we put them in a vacuum chamber, that pumps out the air. There's no air, there's no medium, and therefore the sound waves can't move from the left tuning fork to the right one. So the answer we're looking for on this one is C, no, because almost none of the energy from here actually makes it over here, and therefore it cannot force that tuning fork to vibrate. All right, practice problem 16. The figure below illustrates the movement of a wave traveling through a uniform medium per unit of time. Which of the following correctly describes the wave? Choose 2 answers. All right, so we're looking at the amplitude of the wave against time. And we see that the amplitude is vibrating up and down, and the wave is moving this way. So that tells us, because the vibrations are in the opposite direction of the movement of the energy, it's a transverse wave. So A looks good. It's not a longitudinal wave. We need to know if either the frequency or the period is 6 seconds. Well, if we start here, notice this wave goes up, it goes down, comes back up, and right here it begins to repeat itself again. So this is one cycle. It takes 6 seconds for one cycle to occur. That tells me that the period of this wave is 6 seconds. The frequency would be equal to 1/6 seconds. So on practice problem number 16, we're looking at answers A and D. All right, so on to practice problem 17. We have a student who wants to determine the speed of sound in air in Denver, Colorado. In order to determine the speed, the student performs an experiment to find the resonant frequencies in a tube that is closed at one end. So much like the problems we worked earlier. The student performs the experiment 5 times per day for a week and gets different results on each day. Which of the following experiments would help the student determine the reason for the different results? Okay, A, using a different frequency. B, using a tube of a different length. C looks like the correct answer here, because what you got to remember is that the speed of sound varies with temperature. As the temperature of the air increases, the speed increases. So we're looking at C as the best answer here on practice problem 17. All right, practice problem 18. The graph shown below depicts a transverse wave traveling through a stream. What's the period of the wave? Some of you are going to not pay attention to the graph, and you're going to say, okay, the wave goes up and down and back up, and it starts over here, so the period is 40. Well, you'd be incorrect if you did that, because this is not a displacement against time graph. This is a displacement against distance graph. So what this is saying, as the wave displaces this far and a point displaces this far, the wave actually moves this far down the stream. This particular graph does not give us the information we need to determine the period or the frequency. This particular graph, a displacement versus distance graph, would allow us to determine the wavelength. It will not allow us to determine the period or the frequency. So our answer here is D. All right, so we're back to number 19. Looks like the same problem, but this time the problem is asking us to find the wavelength, not the period. So again, we see that the wave starts here, it goes up, it comes back down, and then right here, it begins again. So here we're looking at one complete cycle, one complete wavelength, and that wavelength is 40 centimeters long. So this is 40 meters. This should say 40 centimeters. Let's get that correct. So our answer here is answer A. All right, so this time we have two ropes made of the same materials, but of different lengths, and they're attached to the same wave generator. Both of the ropes are attached to a heavy ring stand on the end opposite the wave generator. The two ropes have the same tension. The wave generator generates a transverse wave and is adjusted so that a first harmonic wave appears on the longer string. Why is there no standing wave generated on the shorter string? Well, if we look through our answers here, the best answer is B. The length of the string must be a multiple of 1/2 the wavelength for a standing wave to form. And the shorter string just doesn't meet those conditions. So again, standing waves can only form on strings that have lengths that are multiples of 1/2 the wavelength. All right, so practice problem 21, the graph shows the displacement versus time for a single particle of a uniform medium as a wave passes through the medium. What's the frequency of the wave? So we're looking at a displacement against time graph. That tells us that from this graph, we can find frequency, we can find period. If we start at this point, the wave goes down, it goes up, it comes back down, and then right here, that wave begins to start over. So this portion is one complete wavelength. And for that to happen, it took 0.05 seconds. Well, that means that the period is 0.05 seconds. Well, we're looking in this case for the frequency. We know that frequency is 1 over the period. So 1 over 0.05 seconds. And when we do the math on that, we end up with a frequency of 20 hertz, 20 cycles per second, 20 waves per second. Answer B looks good for practice problem number 21. All right, so same graph we used on the last problem. Remember, this is a graph for a single particle in a medium. And all the particle's doing is vibrating up and down. We're trying to find the speed of that particle. So it vibrates down 0.01 meters, and then it vibrates back up 0.01 meters. And it does that in 0.05 seconds. So if we're trying to find the speed, this thing travels 0.01 plus 0.01. So it travels 0.02 meters, and it does that every 0.05 seconds. We know speed is essentially distance divided by time. So if we go 0.02 divided by 0.05, we end up with answer C. 0.4 meters per second is our speed of this particle. All right, so practice problem 23, same graph we looked at earlier. Remember, this is a graph for a single point, single particle in a medium as the wave passes through the medium. And we're trying to find the wavelength of the wave. Now note, this is a displacement versus time graph. If we're going to find the wavelength, we need a displacement versus distance graph, a distance the wave traveled. We don't have that here. That's telling me that this graph will not allow us to determine the wavelength. So our answer on this particular question is D. If we want to find the wavelength from a graph, we need to have a displacement versus distance graph. All right, so number 24. A standing wave in a taut rope of length L vibrates with 6 nodes. And notice if it has 6 nodes, it's going to have 5 antinodes. The dashed line indicates the equilibrium position of the wave. The standing wave pattern was likely formed by the superposition of the following. Remember, superposition essentially means they're placed on top of each other, where they will interfere. So remember that standing waves in a string occur when a wave moves through the string, vibrates, bounces back, and then meets the next wave. Those waves are going in opposite directions. So first of all, any question on or any wave on here that says the same direction, we can probably eliminate that choice. So that would eliminate A, and it would also eliminate D. Our 2 waves need to be moving in opposite directions. So the other thing that we need to look at is the wavelength. Remember that one wave is made of 2 complete loops. So if we look at the length of the string, there's one wave here, one complete wavelength, another complete wavelength, and then a half of a wavelength. So we're looking on this wave at 5 halves of a wave, 2.5 waves on that one string, which tells me that the wavelength of the waves that formed this wave were 2/5 times the length of the string. Only 2 out of 5 were one wave. So knowing that the wavelength of the waves that formed the standing wave were 2/5 times the string length, the answer we're looking for here is B. All right, so the next problem, number 25, an ambulance sits stationary on a straight road. The ambulance's siren produces a steady sound of constant frequency. A student uses 3 sound detectors to determine the effect of motion on the perceived frequency of sound. One of the sensors, A, is placed near the ambulance and remains stationary throughout the entire experiment. Another sensor, B, is placed 100 meters away from the ambulance on the right and moves at 10 meters per second in the direction of the ambulance. The third sensor, C, is placed 100 meters away from the ambulance on the left and moves at 10 meters per second away from the ambulance. Which of the following ranks the frequencies detected by the sensors from highest to lowest? So remember that when a sensor moves toward a sound source, the wave fronts get compressed together. And what the sensor picks up is actually waves of a higher frequency than what is actually being released by the source. On the other hand, when a sensor moves away from a sound source, the wave fronts are stretched out. So the sensor picks up a frequency that's actually lower than the real frequency. So what that tells me is that the sensor that's moving toward the sound source is going to have the higher frequency. That's B. So B is going to have the highest frequency. A is just sitting there. A is going to pick up the real frequency of the source. C, on the other hand, is going to have a lower frequency than the source. So this looks like answer D is our correct answer. This is a good example of the Doppler effect. Motion affects the perceived frequency of sounds that are picked up by either a person's ear or, in this case, by a sound sensor. All right, so this is the last practice problem, number 26. 2 wave pulses on a string approach each other at a speed of 1 meter per second. So notice they're starting off right. Let's think of the center of the waves. So this one's at 1. So after 1 second, the center would be here. 2 seconds, it would be here. 3 seconds, it would be right here. This one's starting at 7. After 1 second, the center would be at 6. 2 seconds at 5. 3 seconds at 4. So their centers are going to meet at the 4 meter mark at 3 seconds. Notice that both of them are pointed up, so their centers are going to meet. They're going to constructively interfere. And remember that the displacement of the combined waves is going to be the algebraic sum of the displacements of the original waves. So those are going to add together constructively, and what we're going to end up with is something that looks like the two combined. Answer C. Forgot about one thing. We have a free response question that we need to look at as well. All right, so we have a string attached to a vibrating machine. So this is the vibrating machine over here with a frequency of 120 hertz. The other end of the string is passed over a pulley. So this would be our pulley right here. And is attached to a weight hanger, which holds a mass of 0.5 kilograms. That would be this. Determine the tension in the string. Well, the tension in the string is essentially going to be caused by the weight of this hanging mass, because it's going to be pulling down. And the pulley will translate that to being pulled across. So the tension in the string in this case is going to be equal to the weight of this mass. Well, we know that weight equals mg. So weight equals 0.5 kilograms times, we'll just use 10 for g. So we're going to end up with a tension force of 5 newtons. Second part, the speed of the wave in the string is related to the tension by the equation, which we'll talk about in a second, where the tension in the string and where Ft is the tension in the string and mu is the linear density of the string. If the linear density of the string is 0.05, determine the speed. So again, this is the equation we're talking about. Speed equals the square root of the tension force divided by mu. And remember that mu is essentially the mass over the length of the string. So we're going to plug in our tension force, 5 newtons. We're going to plug in our mu, which is 0.05 kilograms per meter. We're going to divide that and then take the square root of both sides. And we're going to end up with our speed of 100 meters per second. Next, we want to determine the wavelength of the wave. Well, we'll do that down here at the bottom. We'll have to use the wave equation. We're trying to find wavelength, or lambda. So lambda is going to be equal to the speed of the wave divided by the frequency of the wave. Well, the speed we just calculated to be 100 meters per second. And the frequency is going to be the frequency of our vibrating machine, which is 120 hertz. So we do the math there, 100 divided by 120. Our answer on part C is going to be 0.83 meters. D, determine the length of the string from the point of the attachment on the vibrating machine to the pulley. Well, here's the deal. We know the wavelength of our wave. And remember, the wavelength of a standing wave is made up of 2 loops. So we have 1 wave, 2 waves, 3 waves. So we have 3 complete wavelengths on our string. So to find the length of the string, we're going to say 3 times our wavelength of 0.83. 3 times 0.83 is going to give us about 2.5 meters for the length of our string. And then finally, would you need to increase or decrease the mass on the hanger to produce a lower number of loops? All right, so if we had a lower number of loops, that would mean that the wavelength of the wave is longer. We can't change the frequency. The frequency is determined by the vibrating machine. So if the wavelength gets longer, that means the speed of the wave has to increase. Well, the only way we can increase the speed in this particular string is by making it have more tension. To make it have more tension, we're going to have to increase the mass on the hanger. So increasing the mass on the hanger will increase the tension in the rope, which will increase the speed of the wave going through the rope. And since the frequency can't change because it's determined by the vibrating machine, the wavelength will then get longer. So we're going to need to increase the mass of the mass on the hanger. All right, that's it for our waves practice problems. Hope that helped.